Hi, this is Steve Mackay from Engineering Institute of Technology. Another wonderful set of recordings. This one's on pressure measurement. Again, I don't want to bore you out of your brackets with too much sort of repetitive stuff which is on the slides. I just want to go through the key issues with the pressure measurement and just really highlight some of the issues you need to think about, some of the issues as far as the basic mechanics of pressure measurement. So, what are we measuring and what are some of the terms used? Then I just want to briefly outline the mechanical pressure transducers and electrical transducers. What are they? Sort of typical types that you've got, and there's a vast range. And then just briefly talk about installation and impact on the overall loop. So quite a lot of sort of issues there, and then just sort of wrap it up at that point. But you will be provided with all the slides so you can really have a good time going through it in more detail. The purpose of this presentation is just to give you a bit of a quick run through. And by the way, I've had, I think, 3 attempts at this presentation. I had a problem with scribbling everywhere, and that caused a few little software hiccups. I tend to like scribbling everywhere, as you can see. First of all, pressure is force per unit area, as you probably know from your year 8 high school physics or science. And typically we measure in kilopascals or megapascals, capital MPa. And also millimeters mercury. Mercury isn't as popular as it used to be because it's toxic, as you all know, with the fish that eat mercury. Eating mercury is not a good thing. And pressure pounds per square inch, which you still see used even when you're pumping your tires up with air. You see PSI and kilopascals even in the very metric countries. And just as a matter of, as an aside, you probably remember the 4 to 20 milliamp standard. Well, that's related to the 3 to 15 PSI standard. 15 divided by 3 is 5, and 20 divided by 4 is 5. So it's still around. Other terms we use are absolute pressure, which is reference to a vacuum where there's no air molecules at all. Gauge pressure is referred back to standard atmosphere. And differential pressure, when you hear that, means just really the difference between 2 different pressures. 2 types of sources of pressure, static pressure and dynamic pressure. As you can imagine, static pressure is when you look at the air pressing down on you. Dynamic pressure is the blast of a wind onto your hands. So 2 types of pressures, and obviously total pressure is the sum of static and dynamic pressure. Static plus dynamic pressure. So obviously both add up. Just as far as transducers are concerned, as I said, I just want to quickly highlight the different types. Burden tube, forgive my pronunciation. Helix and spiral tubes, spring and bellows, diaphragm, manometer, which is the one you probably came across in physics quite often, and then single and double inverted bell. So quite a few different pressure transducers in the mechanical range. Basically, the C burden is quite popular. Here's a typical pressure element here. Process pressure comes in through here, and of course, this pivot moves depending on the pressure. So, quite important connecting link over there. So, using air calibrated for air, using liquid calibrated for liquid, that's pretty obvious. You don't use it when you've got lots of shock. And if you're using it for oxygen, you can't calibrate it for oil. Helix and spiral tubes, another approach, 20 megapascals, or 28,000 kilopascals to 500,000 kilopascals for helical. Here's a helical spiral tube, pretty straightforward. Pressure comes in through here, and of course causes the element to move that way, rotate that way or that way, depending on the pressure. Advantages obviously increase accuracy and sensitivity. Disadvantages can be very expensive. Spring and bellows is another one. Here's a spring and bellows switch. Can be used spring and bellows gauge. Atmospheric pressure coming in through here. Of course, causes a change to the linkage movement and, of course, your measurement. Diaphragm, bellows or piston. Just a bit of a slide there. Refrigeration applications. Diaphragm sensor measurements depending on the deflection of the diaphragm. Flexible disc. You need high tolerance dimensions. Here's a simple corrugated diaphragm. Two types, motion balanced, force balanced. Advantage of the diaphragm are you get isolation from the process fluid, good for low pressure, cheap, and a wide range, and pretty reliable, widely used. Manometer is the other favorite one, which, as I say, you come from high school physics, you may remember that. It's a U-shaped liquid-filled tube. Here's a good old mercury is typically used, or you could use water. Here's 1 Pascal, 0.9807 is the atmospheric reference. So your measured pressure comes in here, and your reference pressure is over there. So you look at the difference in pressure. Obviously, the pressure is pushing down, and of course, mercury has a fairly significant weight. Typical applications: spot checks or calibration, low range measurements. Obviously, mercury is toxic, so you avoid it if you can. It's cheap. If you want a higher pressure range, you need mercury. Why is that? Because mercury has a greater mass or weight. Otherwise, single and double inverted bell is the other one. Here's a single and inverted bell differential pressure detector. As far as electrical measurements are concerned, excuse that bong 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 sound. As far as electrical transducers are concerned, strain gauge, vibrating wire, piezoelectric, capacitance, LVDT or linear variable differential transformer, and optical. So it's quite a range of animals there to use. I would say that strain gauge I've used quite extensively as a pressure measurement for level, so it's quite useful for that. Strain gauge, quite easy. Basically, as you know, in a strain gauge, in a Wheatstone bridge, when you deform the strain gauge, metal's deformed, and of course, if you pull metal, a strip of metal out, it gets thinner and the resistance goes up, or if you compress it, it gets fatter and thus the resistance goes down. You do need temperature compensation, so here's an example here, and your output measurements there, Wheatstone bridge. Typical application, force applied to diaphragm, and of course you will see a pressure change will cause deformation of the Wheatstone bridge of the elements, and of course that would then cause resistance changes, and of course Wheatstone bridge maximizes the resistance change and the voltage change. Opportunity is that it's very low, wide range, from 7.5 kilopascals to 1400 megapascals, which is quite an enormous change. Very low accuracy, 0.1%. Small, fast response, no moving parts. Disadvantages are it's a little bit unstable and it's temperature sensitive, so you've got to watch out for that. Can cause problems. Vibrating wire is another one. Electronic oscillator circuit causes natural frequency oscillation of wire. Not going to worry about that. Piezoelectric is another one. You know, the piezoelectric crystals. When you deform a crystal due to a force, you will see the rate of change of deformation gives you an electrical output. Used in crystal radio sets as well. Piezoelectric, very good accuracy, 0.075%, which is very low, which is a good accuracy. Small size, robust, fast response, less than one nanosecond, 10 to the minus 9 seconds. It's a dynamic sensing device, so that's the only disadvantage. So here's a cross section of a Rosemount sensor. Capacitance is another one, and again, it's quite clever. This one here, you're looking at the reference temperature, and the process pressures coming in there and the reference pressures coming in over here. That change in capacitance there is compared to a higher frequency oscillator from here, and the voltage measurement is what you look at there, and this is obviously a capacitance bridge. Two capacitors which are changing. Very low inaccuracy, 0.01 to 0.2%. 80 pascals to 35 megapascals, so really good solid range. Linear, which is obviously really useful. No linearization required. And disadvantage again is temperature, strange capacitance problems. LVDT is the other little animal that's floating around. So here you've got your high permeability coil, LVDT, and any deflection here, you will see that change in the LVDT. Good old transformer. Finally, optical is another type. Vane moves in front of an infrared beam, and that will indicate the position and thus the pressure. Just a few installation considerations to bear in mind of. Obviously, location of connections, isolation valves, impulse tubing, test and drain valves, the construction, temperature variations, as we discussed, can be a big impact. Remote diaphragm seals. Think carefully about process flanges and additional hardware. So these all need to be thought through carefully before you jump into your actual installation. Just a few summary of the different animals that you need to think about. And finally, just think about the overall control loop when you're looking at the response time. So if you've got any response delays, that adds to the overall response of the overall loop. So your PID loop, control loop, a great delay in response or a sluggish response could impact on your overall control strategy. So watch out for that. Okay, that's me, Steve Mackay. Thank you very much for tuning in, and hopefully this was of use to you from the Engineering Institute of Technology. Sorry I overshot on time. Any questions, please ask, and I'll be only too delighted to ask. Thank you. Answer. Steve Mackay, Dean of Engineering, Engineering Institute of Technology, signing off. Thanks very much. Bye.